Hello my dear children of class 11 science. Today again I welcome all of you through this mode of teaching. We are following YouTube mode, and in today's class we do continue with the chapter that is flow of liquids, and even we do continue with the topic that we started in the last class and in the last YouTube video, that means the class which was taken last time, yesterday. It was up to Stokes Law. We had just stated Stokes Law, and we understood actually what Stokes Law measure and how the terminal velocity of the body, a ball, occur when that ball or spherical ball moves in a liquid. Okay, so now in today's class we do expression of that terminal velocity from the Stokes Law. Okay, from the what law? Stokes Law. Now for this particular topic to learn, okay, to derive the expression terminal velocity, so I take a liquid. I take a what? Liquid. So suppose there is a liquid out here. So I'm just drawing this way. Okay. Consider there is a liquid contained in a beaker. Suppose there is a liquid contained in a beaker. Okay, there is a liquid contained in a beaker, and I am dropping the ball, spherical ball, okay, a very small spherical ball into this liquid. Okay, so what I do, I consider that there is a spherical ball which is usually small, we take small, smooth and rigid, and when I drop it, it moves slowly. It moves what? Slowly. So when it falls, okay, when it falls, at that stage of this spherical ball, okay, I consider, suppose that stage will be at this position, okay, and this spherical ball has a radius, as this spherical is usually what in shape? Spherical shape. That's why it has a radius also. So once it reaches to that stage of the okay, in a liquid, so that there is a force exerted by the weight of the spherical ball, and with this weight, force is actually the weight or the force due to gravity which acts vertically downward. But this weight is exactly balanced by what? The upthrust exerted by the liquid, and even the viscous force exerted in the liquid in the upward direction. So the net force acting on the ball will be 0. So under this case, this spherical ball falls with a constant velocity. What velocity? Constant velocity. And that constant velocity is also called terminal velocity. And that terminal velocity expression we are going to derive. Now I consider this is the stage where the ball is falling down with a constant velocity in the downward direction, and that constant velocity is B. So B is the constant velocity, and this is called terminal velocity. Okay, but as I said that when ball fall down, it falls with a weight. Okay, the weight act vertically downward, but other than weight, there is a force which act vertical of what? Okay, the upthrust and the what? Upthrust and the viscous force which act vertically upward. Now children, one important thing that you need to keep in mind when we derive this terminal velocity is the medium in which the ball is falling down. Means the liquid which we are taking must be a homogeneous medium. Medium made up of same material. No mixture of any other material. Okay. Means no impurities present in the liquid. Okay. Now the ball which we are taking is a spherical ball having a certain radius, and that radius I consider as what? R. So I write down, let R be the what? R be the radius. The radius of what ball? Spherical ball. So that spherical ball has a radius R. Now this spherical ball, okay, has even a density also, and that density I consider as rho. So look at the symbol we are using. Rho be the what? Density. I am using rho be the density of what ball? Spherical ball. And this spherical ball having density rho is dropped in a what? Is falling in a what? Liquid, and liquid also has a density, and that density I consider as sigma. So symbol I am using out here, children, is called sigma. So sigma is the what? Density of liquid. I consider density of what? Liquid. Okay. And the next part that you need to keep in mind is the liquid is expressed by its nature, and the nature of the liquid is expressed even by the term called viscosity, and that viscosity is called coefficient of viscosity. That means a body, when a body falls in a liquid, there is a relative motion between the layer of the liquid, as you know, and that due to that there is some opposing force exerted between the layer of the liquid, and it is expressed by the term known as what? Coefficient of viscosity. Means liquid has coefficient of viscosity, and that is given by eta. So this is the symbol we use, eta. Eta is the what? Coefficient of viscosity. This is the coefficient of viscosity of liquid. Viscosity of what? Liquid. Now, in order to come to the expression of terminal velocity, let me just again tell you this part, which is important, you need to understand. Okay, as you know, when a body, okay, spherical ball or body, when it just dropped, okay, in from this layer, okay, of the liquid, then it will start falling down slowly. Under this case, the layer of liquid, like say a water, in contact with that ball tends to move with the velocity of the what? Ball. While the layer far away from the what? Far away from the ball remains at what? Rest. Thus, as a result of motion of the balls, when the ball is keep on falling down, means the ball is in instant motion, there is a relative motion of the layer of the what? Adjacent layer of the what? Liquid. Like if I take the liquid like water, there is a adjacent layer of the adjacent motion. There is a relative motion of the adjacent layer of the water. So under this case, what happened? Which force comes into play? A viscous force, and this viscous force which develop in, say, in case of water, which opposes the motion of the ball. The motion is downward, but the viscous force which act between the adjacent layer of the liquid opposes the motion of the what? Ball. Now the magnitude of this viscous force, remember this, goes on increasing. Goes on what? Increasing with the increasing velocity of the ball. So velocity of ball increases. When the velocity of ball increases, the viscous force also increases. But the ball, there will be a stage which will reach when the ball falling down in a liquid at that particular position, where the opposing force, the opposing viscous force, okay, is exactly equals to the net or effective force driving the ball. The effective force which is driving the ball is downward, and the viscous force which opposes the motion of the ball is upward. But these two forces are exactly balanced to each other at that stage. So in that particular stage, what happened? The net force acting on the ball will be 0. So as I said, when the net force acting on the ball is 0, then that ball does not move, acquire any acceleration. When there is no acceleration, means definitely the ball falling down, but with a what velocity? Constant velocity. And that constant velocity is called terminal velocity. What velocity? Terminal velocity. And we are going to now derive the terminal velocity. So children, as I said, there will be a stage which will reach, and this diagram is on that stage where the net force acting on that ball will be 0, and the body is moving with, or the ball is moving with constant or terminal velocity. So when a ball moves with a terminal velocity, say b, what happened? Effective downward driving force is exactly equals to viscous force acting upward. Means these two forces balance with each other. Okay. Now what is effective downward driving force? The effective downward driving force is equals to the weight of the ball minus the upthrust acting by the liquid on that ball. Because upthrust is upward, the weight is downward, but still the ball is falling downward only. See, the ball is not at rest because their body is moving with the what velocity? Constant velocity. That's why the net force acting on the body is downward, okay, but that force is balanced by the viscous force in the upward direction? Upward direction. But the effective downward driving force is equals to the weight of the ball, which is downward, which is more than the upthrust acting on the liquid upward. And that is equals to what force? Viscous force acting upward. Now to calculate this expression, now I calculate weight. Now weight of the ball means mass into gravity. Weight means mass into gravity minus the upthrust exerted by the liquid on the ball is actually given by the volume of the ball. The volume of the ball means spherical ball. The density of the liquid, rho, and the acceleration due to gravity. Because who is exerting upthrust? Water. And water means like a liquid which has density what? Rho. So we can write upthrust even by relation B rho G. B rho G. Okay. And weight of the ball is given by M into G. Where M is the mass of the spherical ball. Equals to, now the viscous force acting upward is given by Stokes Law, and Stokes Law measures the viscous force by the relation 6 pi eta RB. See, this part we have already explained. 6 pi eta RB is the expression of viscous force, okay, when the body moves with the what velocity? Terminal velocity. But children, you know mass equals to volume into density, and volume is the volume of the spherical ball into density of spherical ball is what? Rho. See, volume and density of spherical ball into G minus volume of the same spherical ball displaced by the water, density of liquid and gravity, and this is upthrust. This part we have already learned even in class 9 also, equals to 6 pi eta RB. So you can see what is common in the expression. The common is what? B. I take common B and G. So inside the bracket is rho minus sigma into G equals to 6 pi eta RB. But children, you know sphere has a volume also. So volume of the sphere is given by the formula 4 by 3 pi r cube, and r is the radius. Rho minus sigma G equals to 6 pi eta RB. Now I do the cancellation of this expression. Pi and pi cancel out. 1 r and 1 cube r cancel out, means r square remains. Yes, we can cancel 2 3 ja 6, 2 2 ja 4. So what is remaining in the left hand side? 2 by 3 r square rho minus sigma G equals to what? 3 eta B. 3 eta B. See, 3 eta B. But actually I am making what? B as the subject. If I make B as the subject, then this 3 eta will go in the denominator. So I write on 2 r square rho minus sigma G divided by this 3 and 3 multiply is 9, and eta will go down. So you can see the expression B equals to 2 r square rho minus sigma G by 9 eta. So finally we can see the expression of terminal velocity that we measured is B equals to 2 r square rho minus sigma bracket G by 9 eta. But in this expression you see rho must be greater than sigma, with the density of spherical ball must be greater than the density of water, otherwise that spherical ball will simply float on water or in that liquid. Okay, so that's why in order to make the ball to move down, the density of that ball must be equal to greater than the density of liquid. So from the relation you can see the terminal velocity is directly proportional to r square, square of the radius. Terminal velocity is directly proportional to the square of the radius. Means larger the spherical ball we take, more is the terminal velocity. That means terminal velocity is directly proportional to the square of the what? Radius. Because the other factor basically remain constant. Rho, G, sigma, eta, this will remain constant. That's why when radius of the spherical ball increases, the terminal velocity also increases. Now this concept of terminal velocity and the Stokes law has a practical application. Now just to highlight that what are the application of Stokes law, okay, or terminal velocity, is one of the most important application which was used by one of the scientists called J.A. Millikan's. So listen carefully children, J.A. Millikan's, who actually determined the charge of electron. You know, charge of each electron is 1.6 into minus 19 coulomb with minus sign. And this value which is actually determined by one of the experiment which was performed by Millikan's, the scientist's name was Millikan's, and to perform the experiment by Millikan's, okay, he used this formula known as Stokes formula. So Stokes formula is used to determine the electronic charge, the charge of electron in what experiment? Millikan's experiment, who determined the value of what? The charge of each electron. And children, at the same time, another natural application of this Stokes formula is it is also used to find the velocity of raindrops. The falling of raindrops velocity can also can be calculated by using Stokes formula. Okay, so Stokes formula can also used to find the velocity of raindrops also. So children, I have explained in detail about the Stokes formula, Stokes law with the expression of terminal velocity. Okay, so I request everyone to revise this topic. If you find any difficulties, please let me know. Now in the next YouTube video, we will learn another formula, important Poiseuille formula. Okay, and this formula is basically for the flow of liquid through a pipe, and that you learn in the next YouTube video.